Hello everyone. Today we're going to do a brief chemistry midterm review. I'm going to kind of fly through the material that we will be covering on our midterm. So sit back, relax, work out the examples with me, and look over your notes, and you should be fine for the midterm. So let's start off. Let's talk about chemistry. What is it? Well, it's the study of matter, specifically atoms and how they interact with each other. Like biology deals with life and the beginnings of it and all that stuff. Well, whoop-de-doo. Chemistry is the study of matter, atoms, mixtures, chemical reactions, right? The important things. Another definition that we looked at is scientific theory. So it's the careful explanation of observations as backed up by experimentation. That should be by experimentation and the testing of many hypotheses. So, we first have a problem. All right? And to test it, we use a hypothesis. But once we see that that hypothesis is going to be tested over and over again, we start getting a lot of data. And eventually that data leads us to an explanation, all right? And that is a scientific theory. It is an answer, all right? A scientific theory, it could change over time, but it is a possible explanation, a very careful explanation, backed by evidence, all right, backed by multiple hypotheses being experimented on, okay? Okay, so let's look at the next step. What is matter? Well, matter is anything that has mass. Okay. And we learned about two different types. All right, the first type that we learned about was pure substances. And then we also learned about mixtures. Now, pure substances were elements and compounds. Elements being little tiny atoms of a particular type, and then compounds being a chemical bonded structure of elements, much like CO2 or H2O. It has a chemical formula. It's pure, all right? It is only that compound. And then we looked at the non-pure, the mixtures. All right, and we had two different types of mixtures, homogeneous and heterogeneous. Homogeneous means same throughout, all right? No matter which way you look at it, all right, it looks the same, much like Kool-Aid, all right? I look at it from this side, and I hold the glass at a different angle, and I look at it, and I should only see like a red liquid, because homogeneous looks the same. I cannot distinguish individual parts. Heterogeneous means different. Okay, I could tell between different parts. I could look at it and go and, like, for example, like a pizza, and be like, there's the cheese, there's the crust, all right, there's the anchovies, ew. All right, I could tell the individual parts. The heterogeneous mixtures, they're a lot easier to separate compared to homogeneous mixtures. All right, if I gave you a nice blended chocolate milkshake and said, okay, I want you to separate the chocolate and the milk out of it, all right, you would not be able to do it. But if I handed you a bag of, like, say, different colored rocks and say, okay, put all the gray ones over here and put all the brown ones over there, you could do that. All right, so homogeneous and heterogeneous. Now, these different types of matter, they could undergo changes, all right? And we had physical changes, and we had chemical changes. All right, a physical change means I'm just changing its size, shape, appearance. Like I'm grinding it up, I'm breaking it into little pieces, I'm melting it, boiling it, because we know when we do a state change, like H2O as a solid, ice, and say I melted it, I would have H2O as liquid, water. It's still H2O. That is a physical change. Chemical change, however, makes something new. All right, it makes a new substance. So if I took H2O and it went under, a chemical reaction, some kind of chemical reaction would happen, I would have H2 plus O2. Note, it's two different things. It's hydrogen gas and oxygen gas. All right, it is now a new substance. Throughout this, the law of conservation of energy is still conserved. All right, energy is just transferred. Mass is transferred. Matter is transferred. All right, it's not created or destroyed. It's just transferred to something new. All right, so let's move on and talk about metric conversions. Now, we practice metric conversions extensively. All right, and one of the things that we looked at was this little ladder. All right, our metric conversion ladder has each prefix that we looked at on it. All right, it also had the base units being grams, liters, and meters. All right, so when you see a single letter next to the number, then that's the base unit, either a G, an L, or an M. All right, and to convert between these units, all right, we have to pay attention to where we are moving the decimal. To convert to a larger unit, move the decimal point to the left or divide. To convert to a smaller unit, move the decimal to the right. So we're first going to find our starting point. Then we're going to find our finishing point. We're going to move the decimal that many stairs to get to where we're going. And then we're going to, just simply on our example, move the decimal that many times as well. All right, let's go ahead and work an example really quickly. So say I had 40 centimeters. And I wanted to know how many meters this is. Okay, let's go ahead. Let's first find our starting point, centimeters. So this is my starting point, okay? And let's find our finishing point, meters. This is where we're going to end up, okay? So let's go ahead and count our steps. 1 step, 2 steps. So I moved 2 times. All right, I'm going to move my decimal 2 times as well. So my decimal is right there. And now I'm going to move it 2 spaces in the same direction, left. 1, 2. The decimal is now right there. We do not need that one anymore. And so my answer for this problem is 0.40 meters. So 40 centimeters is the same thing as 0.40 meters. Right, and so we got to look at which direction we're going and move the decimal that many times. The next thing that we looked at was the density triangle. All right, we talked about density. You had to calculate it. We talked about the units. Well, for mass, okay, we got grams. Don't forget the SI unit for mass is kilogram. All right. A common volume measurement is milliliters or centimeters cubed. They're the same thing. And density, of course, would be either grams per milliliter or grams per centimeter cubed. It's whatever the mass unit is divided by the volume unit. Okay, so we look at our triangle and we could see every single equation that we need. All right, we just got to figure out what it's asking for. So let's go ahead and take a look at this word problem right here. Okay, so it's saying, let me get my highlighter out. If the mass of an object is 50 grams, okay, and its volume is 10 centimeters cubed, then what is its density? So we are looking for density. We do not know what it is. So if we look over here and we cover density up, then we see that it is mass divided by volume. So density is mass divided by volume. And then we just plug and chug into our equation. So we got the mass right here, it's 50 grams. Divided by the volume right there, 10 cm cubed. Okay. And so what we get is 50 divided by 10, which is 5 grams per centimeter cubed. All right, note I have my unit that matches up with what I use throughout the problem. Okay, if you have a calculator, you might need to use it, but we just look at our triangle, figure out the equation that we need, and then plug and chug. All right, let's talk about significant figures. Now, I taught you the Pacific Atlantic method. So say we had some number, and you will always get some number that you have to figure out the number of significant figures for. All right, we talked about how this is kind of like the country, okay? And you got the Pacific Ocean over here. You have the Atlantic Ocean right there. P stands for Pacific. It also stands for present. The decimal is present. Atlantic, A, also stands for absent. There is no decimal. It is absent. Okay, so the Pacific Ocean goes this way, and the Atlantic goes that way. So what we do is we first identify which area we're going to start. All right, and we're going to work our way either from left to right or right to left. And we will skip over zeros. And we begin counting. So begin counting at the first non-zero. And once we start, we keep counting, going until we run out. Okay, so let's take a look at example number 1 right here. Okay, so is there a decimal present? Yep, right here. Okay, so we're going to begin counting at the first non-zero. We're going to go this way. All right, and we're going to start in the Pacific Ocean, working our way across. So begin counting at the first non-zero. Nope, those are zeros. Nope, that's zero. Nope, that's zero. There it is. There's our first non-zero. So now we're going to begin counting and keep counting until you run out of digits. So 1, 2, 3. We fell into the ocean. So this has 3 significant figures, 3 sig figs. All right, let's take a look at our next example. Okay. Look at this. There is no decimal. It is absent. So that means we are going to work our way from right to left. We're going to begin counting at the first non-zero. Can't start there. Can't start there. Can't start there. Can't start there. There it is. There's our first non-zero. So that's 1. And then we keep counting until we run out. 2. We ran out of digits. So that is 2 sig figs. Okay, so make sure you look at it, look to see if there's a decimal, and then follow along. All right, so now we're talking about Ape Man. All right, now we are trying to figure out the number of protons, neutrons, and electrons. Remember, protons and neutrons make up the nucleus. The electrons fly around in that electron cloud around it. Okay, so what does part of Ape Man stand for? Well, A is equal to P is equal to E. This is the atomic number. Is equal to the proton number equal to the electron number. All right, that means if you find out one of these, you have all 3 of those as an answer. All right, and how do you figure it out? Well, you look at the periodic table. All right, so say we have neon, which has the atomic number of 10. So right there, that is your atomic number. So if this is 10, this is equal to 10, and that is equal to 10 in a balanced atom. Okay, well, what about man? What does it stand for? Okay, well, M stands for mass number minus the atomic number equals the number of neutrons. So now I'm introducing something called a mass number. And mass number is simply protons plus neutrons. It is not this thing at the bottom. Okay, that is the average atomic mass. It is not that. The mass number is the number of protons plus the neutrons. And if we take the mass number minus the atomic number, which is the same thing as P, it will give us what N is equal to. All right, and if we're trying to find mass number, then we just add up the number of protons and neutrons. So I'm going to give you one. I'm either going to give you the mass number and the number of neutrons, and you have to find the others. All right, so carbon 14. All right, this is something called an isotope. An isotope is the atom of the same kind that has different number of neutrons. This means it has a different mass number as well. All right, isotopes are so an isotope of carbon and another isotope of carbon, they're still carbon. They just have a different amount of neutrons, so they have a different mass. All right, so carbon 14. All right, if we look at carbon 14, this right here, and that's a horrible little arrow, is the mass number, aka the protons plus neutrons. Okay, that's the mass number. We can still figure out all the information that we need to from this. So if we look up carbon on our periodic table, we can still figure out the atomic number. All right, so we can easily look up that it has 6 protons. All right, which means it has 6 electrons. But how do we figure out the number of neutrons? Well, we got to pay attention to the mass number. We know that M minus A is equal to N. Okay, well, this is the mass number right here. All right, so 14 minus the atomic number, which is 6, will give us the number of neutrons for this isotope. It is 8. Dun, 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 dun. So this right here would be 8. Okay, it's still carbon, but it has a different amount of neutrons. That's what isotopes are. Another way that we looked at isotope notation was the big symbol, the atomic number, and then the mass number up top. All right. This being the mass number, this being the atomic number. Okay, so we had 2 different ways of looking at it. All right, now we talked about 3 different decay particles when we were looking at the nuclear equations. All right. We had the alpha particle, and it looked like a helium. All right, it had a mass of 4, 2 protons. Okay, it was also the slowest one, the least penetrating. All right, it's kind of a big chubby one flying through the air. Okay, well, what about the next one? Well, it was beta, and it was like a little an electron. All right, so it had a mass of 0. All right, a symbol E, and a charge of -1. All right, it was a little bit faster, but it was still not the fastest. And that would be gamma, which is like pure energy. Okay, it's pure energy, which means it has no charge. It can penetrate a lot of things, and it is the most dangerous of the 3. Gamma radiation is a bad thing. All right, and from this, we learned from our example right here to balance nuclear equations. Okay, now I want us to look at this example. Okay, so on the midterm, you were gonna have to figure out like what's missing and stuff, but I just want to explain how these problems are done. So if we look at these problems, it's like we have a general algebraic equation. Okay, we have a top problem and we have a bottom problem. Arrows are kind of like equal signs. And so what this is saying, let's take a look at it together, is I have 14 is equal to 14 plus 0. So 14, that's the highlighter. 14 is equal to 14 plus 0. Okay, the bottom one is 6 is equal to 7 plus negative 1. Okay, so 6 is equal to 7 plus a negative 1. So 6 is equal to 7 minus 1, and we know that that is true. Because of these symbols right here, we can see that this is going to be an E. Okay, and so we just fill in the dot. Okay, it's either going to be a 4-2He, an alpha particle, a 0, -1, a beta particle, or in some cases, a neutron going flying off. Okay, so you just solve it like you would algebra. So if I had an example of, say, 14 is equal to x plus 3, then I could solve this to figure out that x is equal to 11. And so 11 would go right here. Okay, so we just solve it like we would in algebra. All right, so let's take a look at the periodic table. Ooh, we're moving right along. It's broken apart between metals and nonmetals. All right, but we were going into electron configuration. We talked about the s orbitals over here, the p orbitals right there, the d orbitals, and the f. All right, these blocks, the s block, the p block, the d block, the f block, could hold a certain amount of electrons in each energy level. All right, but we look at the s, we got 1, 2, and that energy level. So s could hold 2, p could hold 6, and d can hold 10, f 14. When we drew orbital notation, that represented, the S was represented by an up arrow and a down arrow. A P was for 3 pairs. D had 5, and then F had 7. Okay? So we had our S block, P block, D block, F block. And it just depends on where it is on the period. When we practiced writing electron configurations, I gave you a little cheat sheet that you could use on the midterm. All right, also looking at this right here. All right, the first thing that we got to do is find where we were, find our exit ticket, or our ending place. For carbon, we're going to end up right here. And then write the whole electron configuration to get to that point. All right, so we know we're going to start right here. This is our starting point. Okay, we're going to go through this 1s2, both of them, so we 1s2. All right, it's like our ticket at a football game. We're trying to find our seat. We got to go through each row till we get to ours. All right, so once we get right here, we go start over at the new row. All right, so we go through both the 2s's. 2s2, and then we make our way through the 2p's. We don't make it to all of them because we're trying to get to this point right here, so we go through 2p1, 2p2. So 2p2, that's carbon. All right, if you could find this in seat number, like your ticket at a football game, then you kind of could look at this thing and go through each section and write it down whole. All right, we learned a couple shortcuts that you should probably review. All right, and then lastly, let's look at some periodic trends. All right, atomic radius. That's simply how big an atom is. All right, so we look at it, we look at the nucleus of some, it might be like this, some might be a little bit bigger. Well, how does this shape up on the periodic table? What does it look like? Well, okay, the largest ones are right here. The smaller ones are right here. So as I go down, it gets bigger. As I go left, it gets bigger. Okay. Well, everything else is the opposite. All right, like electronegativity. All right, electron affinity, ionization energy. The biggest values are in the top right. So as we go to the right, it gets bigger. And as we go up, it gets bigger. Okay, so use your notes. Look at this right here. Okay. An example would be, so say I had 3 elements in a row, and I asked which one has the greatest electronegativity. We know as they increase, it gets bigger. As we increase atomic number, as we go right across the period, it gets bigger. So this one right here would be the largest electronegativity. Okay, it's the opposite of the atomic radius. All right, so looking back at all this, make sure you have your notes, your study guide ready, because the midterm is coming up.